Continue. Just saw the recording in progress. All right. So hello, everyone. My name is Alberto, and today I'm going to be talking to you a little bit about some algebraic structures, specifically groups. And my goal today is to kind of motivate why you would want to use groups. First of all, what they are and why you would want to use them to talk about problems in combinatorics and in discrete math specifically, because they allow us to count things that normally wouldn't be at face level when we talk about some objects like sets or graphs or stuff like that. And yeah, so let's get right into it. So some of the so I have a question for you guys. So in the chat, or if you guys want to unmute yourselves and talk out loud, what are some ideas that you guys have about what algebra is? So what is algebra to you guys? Yeah, so with Zoom, it's kind of weird because I can't see if anyone's typing, but I'm gonna. All right, so manipulating equations. I like that. Okay. Anyone else have some ideas? Study of symbols and rules to manipulate them. I like that. Yeah, x plus 2 equals 3, solve for x. Good, good, right? So everyone seems to be having this idea that there's some rules to manipulating some symbols and that we can use them to maybe solve some equations. So that's absolutely right. And that's a big part of what drives the study of algebra and what motivates us to create these definitions. And when we're studying algebra, there's this word that we use that is kind of the umbrella for group theory and ring theory and the other kind of stuff that falls under algebra, which is abstract algebra. So we want to take kind of the ideas that apply in certain places, and we want to generalize them to work over anything that has a specific set of properties. But this word abstract can sort of seem a little bit intimidating to people who don't really aren't really familiar with the motivation itself. And there's a bunch of definitions that you have to memorize and stuff. So I would like to motivate some of that in today's talk also. So we're going in with the mentality that we want to solve equations and we want to have a rule to work with some objects, right? And so here's some basics. The first thing we want to talk about is if S is a set, what is an operation on that set, right? So Harshit put in the chat x plus 2. So what's plus, right? Plus is an operation, it's addition. And we take two numbers, and when we add them together, we get a third number, which is their sum. And so an operation, just in a general sense, is a function that takes in two elements of a set and gives us a third one, which we call either their sum or their product, depending on what we're calling the operation, right? And usually, if we have a symbol for the operation, this is a binary operation, sorry, binary because we're taking two elements. And if we have a symbol for the binary operation, we usually put it in between the two elements, right, as seen here. So we have this pair a comma b maps to a plus b and or a times b, right? So let's go over some examples of some binary operations. The integers has an operation that we all know and I hope love called addition, where if n and m are two integers, the sum is denoted n plus m. This is a binary operation because it takes two integers and the sum is also an integer. On the set of vectors in Euclidean space, or R3, which is the set of all ordered triples of real numbers, we have an operation called the cross product. And you don't really have to know a lot about the cross product. The point is just that if we take two vectors and we cross them together, their cross product is another vector in three-dimensional Euclidean space. So that makes it a binary operation. And whenever we talk about examples, it's also useful to have some non-examples in mind. So here are some things that are not binary operations. So on the natural numbers, which in Math 102, we learned to be just the whole numbers 1, 2, 3, 4, 5, and so on. And sometimes we include 0, but that doesn't really matter here. the subtraction, we can subtract natural numbers from each other, right? So m minus n is the difference of two natural numbers. But what happens is that the difference between two natural numbers isn't always a natural number. So for example, 2 minus 3 is -1, and -1 is not a natural number. So this function would take pairs and map them sometimes to natural numbers and sometimes not, right? And so we need the codomain to be the set that we're doing the operation on. So this is not a binary operation. Another example is if we have the set of all square n by n matrices of real numbers, right? And we call that mn over the reals. We have the operation of transpose, right? So we can take a matrix, and if we swap the rows and the columns, right? So we take all the columns and make them into the rows, then that's called the transpose of a matrix, okay? And so that is an operation in the sense that the transpose of any square matrix is another square matrix, but it's not an operation in the sense that, it's not a binary operation in the sense that it only takes one matrix to get a transpose, right? It doesn't take two. So we would like to study spaces in which we're composing two things, right? Okay. Any questions before we move on? Questions about what an operation is, maybe some examples you want to ask about whether they're operations or not? Okay. I'll be looking at the chat just in case, but let's move on a little bit. All right, so we're going to look at a special case or a special kind of operation, right? So if we have a set A, any bijection from A to itself is called a permutation of A. And I'm sure many of you have heard this word before. So here's just what the formal definition is. Any bijection from a set to itself is a permutation. It doesn't matter what the set A is, right? If you take two bijections, we learned in Math 102 that composing two bijections, and what does composition mean? It just means if you have two functions, you just apply one first and then apply the other one to the image of that first one, right? The composition of two bijections is itself a bijection, okay? And so this means that function composition is a binary operation on the set of permutations on a set A, right? So S sub A is just what we call the set of permutations of A, right? And just as a special case, if A is the set of numbers from 1 up to the number n, then we call, instead of writing SA, we write Sn, okay? So for example, in S3, we have the permutation that fixes every element, right? So just 1 maps to 1, 2 maps to 2. This little funky arrow with the line on it just means maps to. We have the permutation that swaps the numbers 1 and 2. So 1 maps to 2, 2 maps back to 1, and 3 just gets mapped to itself. The permutation that swaps 3 and 1 and fixes 2, and on and on and on. And here's a question for you guys. How many permutations are there in S3? Does anyone know? 3 factorial, right? So how did you get 3 factorial? Or why is there 3 factorial? That is the correct answer, though. Right. Let me see if I can annotate. It'd be useful. So if I write on the, what is this? If I write on the slide, can you guys see it? Yeah, exactly. So it's 3 factorial because when we want to make a permutation, we need to choose all the images of each of the elements, right? And so if we have the numbers 1 through n, 1, 2, 3, blah, 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 all the way to n, we have to choose the images, right? And so if we choose, let's say A1 for the image of 1, if we were to choose A1 for the image of 2, then that would mean that our function isn't a bijection because 2 things map to the same element, okay? And so here there are n choices. And so I'm just gonna put that in parentheses. Here there are n minus 1 choices and blah, 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 all the way up to here there's only 1 choice, okay? And so when we're trying to find out how many total outcomes there are, we multiply the number of choices at each step, right? And so if we multiply n times n minus 1 times n minus 2, blah, 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 all the way to 1, that is n factorial. So in fact, for any n on S, in S sub n, there's n factorial permutations. Okay. Oh, I didn't know. So how do I clear? Guess I'll have to erase it. Okay, that's good to know. Okay, so here's some notation, right? There's a special kind of permutation that we call a cycle, right? So if we start with 1, then 1 goes to 2, and then 2 goes to 3, then 3 goes to 4, and then we end up back at 1. So 4 goes back to 1. We call this a cycle, right? And so we can write cycles with this notation where we write them inside brackets. And the way we read this notation is that for any number, if it's not the last number, that element maps to, we call it an entry. That entry maps to whatever the entry to its right is. And if it is the last element, then it just maps to whatever the first element is. And so, for example, in this cycle, if we wanted to evaluate, this is just a function, by the way, so we can evaluate it. And so if we want to evaluate this on the number 2, what would that be, right? So we take a look at 2 and we see whatever is to its right. This is just 3, okay? And so here's a kind of a weird question, but what happens to if we evaluate this on 8, right? So 8's not in there. What should we do? Any ideas? There's no right or wrong answers, right? So like I haven't told you what it should do, but what do you guys suggest?
I'm assuming it's something like mod 8 mod 4, like we move 8 steps to the right, and once we get to 4, we go back to 1, and we keep taking steps.
Okay, so that's an interesting idea, and that would kind of make sense here where we have every element from 1 through 4. But like, for example, what about something like 1, 5, 9, right? On 8, what would that be? Like it has to work on the general case, but I like that idea. So 8's not in there, but all we know is 1 maps to 5, 5 maps to 9, and 9 maps back to 1. This is still a cycle because like we go from 1 to 5 to 9, then back to 1. So it wraps around. So that's still a cycle. But what would it be when evaluated on 8? So we have an idea in the chat, says add to the beginning and to the end. So you're saying we should make it a new cycle, right? It's actually not that, but that's really interesting. It's actually way simpler. So I'm kind of trolling you guys. It's actually just maps to itself, right? Whatever is not in the cycle, it means the permutation that the cycle describes just fixes that number. And the reason why we take this convention is that when we're talking about S3, right, the permutations that permute the numbers 1, 2, and 3, we can use cycles whose entries are the numbers 1, 2, or 3. But when we talk about S100, there are permutations that will only permute, 1, 2, and 3. Like for example, in S100, we have the permutation that only swaps 1 and 2. And we won't want to have to write all of the numbers from 1 to 100 just to describe a swap between 1 and 2. So we actually only write the numbers we're swapping, and whatever numbers we're fixing, we don't write. Does that make sense to everyone? And so this notation kind of generalizes, and it's easier for us to see like S3 as maybe a subset of S10 or S100, right? So any questions? I'm gonna start erasing this so that it doesn't show up on the next slide. Okay, so let's move on. And I'll check the chat again. Right. So in general, if we have the cycle A1 to A2 to A1 to A2 to AN, and then back to A1, it just means A1 maps to A2, A2 maps to A3, blah, 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 all the way to an minus 1 maps to an, and then an maps back to a1. Okay, two cycles, a1 through an and b1 through bm, that don't share any entries, we say they're disjoint. Okay, and so try to convince yourselves for a second that if I multiply two cycles, or in this case, not multiply, but compose two cycle permutations that don't share any elements, then that composition, it doesn't matter in which order I do it, right? So if I do, let's say F and G are two two cycle permutations that are disjoint. So this is what I'm trying to say, right? So if I compose F first and then G to the right, or if I compose G to the left of F, then they're the same thing. Why? Because the first cycle doesn't touch any of the elements that the second cycle touches, and vice versa. So actually, it doesn't really matter in which way you evaluate them if they're disjoint, right? So the areas of the set that are affected by one cycle are not affected by the other. And so we have a theorem. Any permutation in Sn can be written uniquely, up to reordering, of course, because the order of composition doesn't matter, as a composition of disjoint cycles. Okay, and so we actually have an algorithm to do this. So here's an example. Take the permutation that maps 1 to 2, 2 to 4, and 4 back to 1, and 3 to 5, and 5 to 3. And so here's the algorithm. We start at the smallest number that we haven't used yet. In this case, it's 1. Then we see what 1 maps to. In this case, that's 2. We write 2. And so now we see what 2 maps to. And it maps to 4. But 4 maps back to 1, right? So we have to close that cycle. And now we compose it with the cycle starting with whatever is the smallest thing that we now haven't used, right? And that's 3. And what does 3 map to? 3 maps to 5, and 5 maps back to 3. And so this is what this permutation would be written as in terms of disjoint cycles. So this is really important that you guys understand, because it's going to be used around in the rest of the presentation. So does anyone have any questions at this point? Don't be embarrassed to also, unmute and ask some questions if it's too much to type or something. Okay, so while you guys are typing your questions, I'm not going to move on, but let me just highlight something important. This kind of gives us a way to write permutations, quote unquote, in their simplest form. What do I mean by this? So if I have two permutations that aren't disjoint, let's say 2 maps to 5 and 5 maps to 3. Okay, I can rewrite them as the product of disjoint cycles, right? So right now they're not disjoint because they share the entry 5. Okay, but I can write them using this algorithm as a product of disjoint cycles, which is kind of their quote unquote simplest form. Okay, so how would I do that? I pick the smallest thing I haven't chosen yet, right? So 1 is the smallest thing. What does 1 map to? Right? I check this cycle, 1 maps to itself because it's not in there. Okay, and then I check this cycle, right? We check from right to left because that's the order in which we evaluate functions, and these cycles are nothing more than functions. What does 1 map to in the second cycle? Well, nothing. It maps to itself because it's not there, right? And so 1 maps to itself. But before we said that if something maps to itself, we don't write it, right? So we just move on to the next number. What's the next smallest number? Is 2, right? And 2 is in there, right? So we're going to write 2. What does 2 map to here? Itself, right? And so what does 2 map to here? 5, right? So 2 maps to 5 in the product of these. So we write 5 here. So we go on, 5 maps to 3, 3 maps to itself, right? So 5 maps to 3. And here, 3 maps to 5, and 5 maps to 2. So 3 maps back to 2, and we close the cycle. Okay. So the only thing missing from 1 to 5 is 4, right? So what does 4 map to? Well, 4 maps to itself here and here. So we don't write it, right? So the entire kind of this is a product of disjoint cycles because it is just, namely, it's one cycle. So trivially, it is a product of disjoint cycles. And we've written this, it's the same permutation, but now it's written in the simplest possible form. And this, I want you to kind of think about it as, how do we do arithmetic with cycles? This is the answer, right? So we take two cycles, compose them, write it in the simplest form, and that's the answer, right? So this is how we do arithmetic in the set of permutations. Now, does anyone have any questions? This will come back. If anyone's confused, right, this will come back. Just bear with me for a second, and I will answer any questions as they pop up, right? Okay. So let's move on. The question now is, can we solve equations using this arithmetic, right? So if we have an equation that says, if I compose 1, 2, 3 with some permutation x, and that gives me 1, 5, 3, can I solve for x? So what do you guys think? How would we approach this even? Okay. And the kind of way we would approach this, let's think about how we would do it with numbers. So if we want to do algebra with numbers, we have 5 times x is 13. Okay. And so how would we solve for x? Well, we have a tried and true method of, let's multiply by the reciprocal to isolate x on one side of the equation. Okay. And what's the reciprocal? So why do we care about the reciprocal? Right? If we multiply 5 by its reciprocal, 1 over 5, we get 1, right? And multiplying by 1 does nothing, right? It just leaves x the same. And so that allows us to isolate x by itself on one side of the equation. And the solution is whatever's on the other side. So what are the 3 things that we're kind of using here? So first of all, we're multiplying by an inverse to cancel out, so to speak. Second is we're using the fact that multiplication is associative. So it doesn't matter what side kind of the bracketing we evaluate first, the answer is the same. So we can move the brackets over to 5 and 1 over 5 and cancel it out to give the identity, which is 1, right? When we multiply by the identity, we just get x back. And it's as simple as that. We've isolated x on its own side of the equation. So these are the 3 elements that we're going to need in order to be able to do algebra with permutations. So let's ask ourselves these questions. Is composing permutations associative, right? So let me write it in the chat. If I have 3 functions, f, g, and h, is this true? Right? Is f compose g in parentheses compose h equal to f compose parentheses g compose h? Right? So by definition, it is true, right? Because we're just evaluating the 3 functions. It doesn't really matter if we evaluate the composition first on the left or on the right. There's only one way to do the evaluation, which means that this is associative. Is there an identity permutation? Well, yes, there is, because it's the identity function. The identity function, what's a permutation? A permutation is just a bijection from a set to itself. And that's exactly what the identity function is. It's injective because it just maps everything to itself. It's surjective because everything gets mapped to itself, so everything gets mapped to. Okay, so it is a bijection from a set to itself, and therefore it's a permutation. Do all permutations have inverse permutations? Okay, again, from Mat 102, we know that all bijective functions are invertible. Okay, and the inverse of a bijection is itself a bijection. So the inverse of a permutation is again a permutation. So the answer to all of these questions is yes, right? And so we have the 3 ingredients: associativity, identity, and invertibility that allow us to do algebra. So here's a question for you. What is the inverse of this cycle, 1, 2, 3? So I'll wait for one of you guys to answer this before we move on. And by the way, can everyone hear me still? I could be just talking to, oh, all right. So I see some answers. That's exactly right. So it's 3, 2, 1, okay? And why? right? So if we evaluate it, 1 maps to 2, and 2 maps to 1. So 1 maps to itself, right? 2 maps to 3, and 3 maps to 2. So 2 maps to itself, and the same is true for 3, right? And so since we're mapping everything to itself, therefore, this composition is the identity. And so we've done it. We found the inverse of 1, 2, 3. Okay, so let's go back to this problem. If we compose 1, 2, 3 with x and we get 1, 5, 3, how do we solve for x? Let's try the same method as before. Okay, so we multiply 3 to 1 to both sides on the left, right? Because in general, composition of functions isn't commutative, so it matters whether we multiply to the left or to the right. But we don't worry about commutativity here, just associativity. So we multiply to the left, and 3 to 1 composed with 1, 2, 3 is the identity, right? And the identity composed with anything is that anything, right? And on the right, everything we're doing is just rewrite 3 to 1 composed with 1, 5, 3 in its simplest form using the algorithm that we had before. And voila, we've solved this equation. And even though we're not dealing with numbers, all we needed were these 3 ingredients, and we were able to solve some equations and do some algebra, right? So this is where the definition of a group comes from. Okay, so let G be a set with a binary operation, and we usually write that as times, but sometimes, for example, when we can commute, we write it as plus. And we need to have these 3 properties. It needs to be associative, so it doesn't matter how we bracket our expressions. It needs to have an identity, which means that there needs to be some element which, when composed with anything else, fixes that anything else that it composes with. And every element needs to have an inverse, okay? And so a group we can think about in some way as the kind of nicest or simplest way or simplest structure which allows us to do algebra. So I'd like to pause for questions again, if anyone has any questions before we jump into some examples. Okay, I'll take that as a no, and we can move on. Okay, so do you guys think, is the integers a group under addition? Okay, and so how would we check this? So what would be the identity and what would be the inverses? Okay, so someone says yes. So what's the identity under addition for the integers? 0, that's right. And so, and what's, for example, the inverse of 5? -5. Yeah, so negatives are inverses and the identity is 0. And of course, we all know that addition of integers is associative, so that doesn't really bother us. And so what about R3 with the cross product? Is that a group? And what about addition of vectors, right? Okay, so let's think. Is the cross product associative? It's actually not. Yeah, so the cross product is not associative, and I'll leave it as an exercise for you guys to figure out. But yeah, the cross product is not associative, so this is not a group. But what about vector addition? Is vector addition associative? Yeah. And do we have inverses? Okay. And what about the identity? So the 0 vector is the identity, just the negative of any vector is the inverse. And in fact, all vector spaces, just because of the vector space axioms, and you guys can go and check, any vector space is a group, and it's a special kind of group that's called a commutative group or an abelian group, which just means that it doesn't matter in which order you do the addition. Okay. Is the natural numbers a group under addition? Now, so who says yes, who says no? No. Okay, so I see some people say no. Why? No inverses, exactly. So addition of negative numbers, you would cancel that out or you would invert it doing subtraction. But as we said before, subtraction of two natural numbers doesn't always give back a natural number, right? So this is not a group. What about the integers under multiplication? Is this a group? Okay, so no again, and why? Yeah, exactly, no inverses, right? So the only two numbers that have multiplicative inverses are 1 and -1. So that obviously makes it not a group. What about the rational numbers under multiplication? Is that a group? Okay, so what would be the inverses? What would be the identity? So I have, okay, so identity is 1. That's true. 1 is a multiplicative identity. What about inverses? Does every element have an inverse? Okay, so what's the inverse of 0? What multiplies by 0 to give 1? Yeah, so this was kind of a trick question. Q is not a group under multiplication. Yeah, I see the never mind. Yeah, yeah, it was kind of a trick question, but yeah, exactly. So Q without 0 is a group under multiplication. That's exactly right. Okay, and so here's an interesting one. So let's take a regular pentagon, and let's label it. Label its vertices 1 through 5, and let's ask ourselves, what are all the symmetries of this pentagon, right? So I'll give you some of them, right? So we can rotate, right? And we see that 5 is now where 1 used to be, so as we rotated the entries clockwise. And so let me just kind of say what a symmetry is. Symmetries are ways we can move the pentagon around so that it covers where it used to be, but not necessarily having the same vertex labels as before, right? So rotating, if you rotate a regular pentagon, it would cover all the space it covered before, but now the vertices are clockwise from where they were before, okay? So there's another kind of symmetry, which is reflection. And as we see, 5 goes over where 2 used to be and vice versa, and 3 goes over to where 4 used to be and vice versa. And this is kind of like taking a line of symmetry through the vertex 1 and reflecting all of the indices through that line of symmetry. Does that make sense? Everyone good with this? Just yes, no, maybe so. All clear, awesome, okay. So let's think about what are all of the symmetries of a regular pentagon, okay? The one we saw before was a rotation where 5 ended up where 1 was, right? But if we rotate a little bit more, we can make 3 end up where 1 was, or 2 end up where 1 was. And so for each rotation, there's one that makes each vertex end up where 1 used to be, including the one that's doing nothing, which just means 1 ends up where 1 is. And so there's 1 rotation for each vertex, right? So that means 5 rotations total, okay? Also, the same is true for reflections. We can pick the line of symmetry about each vertex and reflect about that line of symmetry. So there's 1 reflection for each vertex, which means there's 5 reflections total. And this is actually every single symmetry of the regular pentagon, as far as we're concerned. And so that means there's a total of 10 symmetries. Okay, so how would we compose symmetries, right? Symmetries are actually just functions. They map vertices to other parts of the pentagon, okay? And so if we have, I'm just using this kind of made up notation, which is rho sub I is the rotation, which makes vertex I go to where vertex 1 is, and sigma sub j is the reflection about the line of symmetry to the jth vertex, okay? And we start counting vertices from where 1 usually is, and we go from there. Okay, so let's apply this composition. Okay, so we pick sigma 4, which is the line of symmetry going through 4, and we reflect about that. Okay, now we're doing row 3. And 5 is where 3 used to be when we hadn't done anything. So we actually move 5 to where 2 is now, which is where 1 usually is. Okay, and now we do sigma 3. Okay, so 3 is where it usually is. So we pick that line of symmetry and we reflect around it. And oh, look, we're back where we started, right? So what if we do row 2? That's a big rotation. So if we rotate 2 to where 1 normally is, anyone notice that, this is basically just rotating counterclockwise? Right, so rotating counterclockwise is covered by rotating clockwise, right? So we can just rotate more clockwise, and we can basically rotate counterclockwise. So there's no difference in, picking clockwise or counterclockwise rotation doesn't really affect what we can do. Finally, 1 is where 5 used to be. So row 5 just returns us back to where we were before. So let's notice something. If we take rotations to be clockwise, row 5 just moves the elements, right, the vertices, 1 over clockwise. So we can actually just take row to be a unit rotation, which is row 5, and we can apply it a bunch of times to get all the other rotations. Similarly, doing any reflection is just doing the reflection of about 1 and then followed by some rotations. So we can write any element of this pentagon group by doing some unit rotation or reflection about the 1. And this means that sigma and rho, these two symmetries, actually generate all of the other symmetries. Okay, so if you've done linear algebra, this should remind you of a basis, right? So we're generating the whole space from a basis. This is the same idea as we're generating the whole group from these two elements. Okay, incidentally, also sigma squared is equal to 1, right? Because rotating or reflecting twice over the same vertex in a row just does nothing. So what if we rotate more than 4 times? Okay, let's apply 5 times unit rotation. So what will happen, right? We rotate once, rotate twice, rotate 3 times, 4 times, and we're back to where we started. What does this mean? Right, so if we rotate 5 times, it's just like we didn't do anything. So if we write rho to the 5th power, just means doing a row 5 times. This is the identity, okay? And so since rotations kind of add on top of each other, but rotating 5 times brings you back to the start, this means that composing rotations is just like doing arithmetic modulo 5, right, which we know from Mat 102. We just reduce finding the remainder by division by 5. Okay, now does anyone have any questions? Just want to make sure I'm not losing anyone. Does anyone see why this is true? Okay, I'll take that silence as a yes. Now, what is so special about this? This means that the rotations just by themselves have arithmetic of their own, right? So if we take just the rotations, they themselves are a group. And that group is included inside of our original group of all the symmetries, okay? So this is what we call a subgroup. And so groups can have subsets, right? Which are closed, which means doing an operation on elements of that subgroup results in another element of the subgroup, right? They're closed under this operation. And these are called subgroups, okay? And so for example, the set of rotations of the group of symmetries of a regular n-gon, right? Under composition, like we just explained, is a subgroup. The set of integers divisible by n, right? So if we add 2 multiples of n, the result is another multiple of n. So this is a subgroup. And the set of positive rational numbers under multiplication, right? So the reciprocal of any positive rational number is positive. and the product of any two positive rationals is positive. So this is a subgroup as well of the group of, you know, Q minus the 0. Okay. And so if G is a group and H is a subgroup, we have this special notation, which is really cute, which is we write H is less than or equal to G, right? And so less than or equal to kind of looks like the subset symbol, but it's kind of pointy and it tells us that we're talking about groups. Okay, so now let's talk about a way of studying offsets of a subgroup by some other element of the group. Okay, and this is kind of a dry definition, but there's some examples that are going to explain what this is all about. So let H be some subgroup of a group G, and we pick any random element of G, and then we multiply every single element of H by G. Okay, so this would be called a left coset, because remember, left or right multiplication could be different because we could have something that's not commutative. Okay, and so this is called the left coset of H by G. And the set of left cosets of H and G is denoted by G/H, and we call this G mod H. And we're not really going to talk about why. Actually, just forget I said that. We're not going to talk about it. This is just G/H, right? The set of cosets of H and G. Okay, and so here's an example, right? So if we have the vector space R2, and this is Desmos, right? So if we have the vector space R2, we have the subspace, which is just all of the pairs for which the y coordinate is 0. Okay, yeah, dark mode. And so we can move this line up and down, right? And this is kind of like an offset of the subgroup, which is the real line. And this subgroup just behaves like the real line, but we're offsetting it either by a positive or negative number. Okay, and so these offsets of the real line are the cosets, right? So this would be the subset, which is the real line, minus 0.8. And this would be the subset that is the real line plus 2.5. Okay, does that make any sense, right? And so, for example, if we have n times z, which is the set of all the multiples of n, we can offset it by some integer. Okay, and notice that if we offset it by 0, it's just a set of multiples. But if we offset it by n, it's also just a set of multiples of n. So this is kind of hinting at that this is just the set of all the residues, or in some way it's the same. Okay, and so what about the symmetries? Okay, so if we have sigma times the group of rotations, okay, then it just gives all of the reflections. And if we multiply the identity, then it just stays the same, obviously. Okay, but notice something. The disjoint union of these are 10 distinct elements, okay? And there's only 10 symmetries. So this is actually the entire group. Is this a coincidence? Okay, is it a coincidence that the kind of cardinality of the subgroup divided the cardinality of the original group? Okay, so let's refresh a little bit from Mat 102. And let's talk about equivalence relations. So what is a relation? So a relation is a set of ordered pairs of S. Okay? And if a pair is inside the relation, we just write A tilde B, which means A is related to B in this relation. So a relation is an equivalence relation if it satisfies these properties, right? So any element has to be related to itself. If X is related to Y, then Y is related to X. So the order of the pair doesn't really matter. And if X is related to Y and Y is related to Z, then X is related to Z. So if we change the word related to the word equivalent, this kind of tells us that an equivalence relation is meant to behave like the equal sign. Anything is equal to itself, right? If X is equal to Y, then Y is equal to X. And if X is equal to Y and Y is equal to Z, then X and Z are equal. Okay. Now, also we have this concept of the set of all elements which are related to some given element, which is called the equivalence class of S. okay? And S is a representative of the equivalence class it belongs to. Now, let's introduce the concept of a partition. So if S is a set, a collection script C of subsets is called a partition if we take all the sets that are in script C and their union is equal to S, and this funny little union symbol that is kind of angled instead of smooth just means that each of the sets in the partition script C are disjoint, okay? So for example, here we use the same symbol because none of the elements in one of the cosets is inside the other, okay? They're disjoint. And their disjoint union is equal to the group of symmetries of the pentagon. So there's actually a really cool thing where partitions and equivalence relations are the same, okay? So if sim is an equivalence relation or tilde is an equivalence relation, the set script C of equivalence classes is a partition of S, right? Since every element has to be equivalent to itself, any element is in some equivalence class. So the union of all equivalence classes is equal to S. But equivalence classes are disjoint from each other because two equivalence classes intersect if and only if they're the same, because two elements are in the same equivalence class if and only if they're equivalent to each other. So this is a partition. Likewise, if C is a partition of S, then every element in S must appear in one and only one element of the partition, okay? And this means that if we define a relation, sim, defined by X is equivalent to Y, if and only if they're in the same element of the partition, this is an equivalence relation. And actually, this equivalence relation, if we start with an equivalence relation and we define this relation on the partition of its equivalence classes, then we get the original equivalence relation back, right? X is similar to Y in the first equivalence relation, if and only if it is similar to Y in the second. So equivalence relations define partitions and vice versa. They're equivalent, okay? Now, if G and H are finite, and H is a subgroup of G, how many cosets are there? What's the cardinality of G/H? Okay, and so this is actually a really satisfying kind of foreshadowing from the notation, as you guys will see. Okay, so we start out, we can cancel out elements, right, using by equations and by using inverses, right? So if we multiply here on the left by G inverse, we will be left with H equals K, which means that for any partition, no two elements can map to the same thing under multiplication on the left by G, in the coset, not the partition. In a coset, no two elements are the same unless they're equal, right? And so the cardinality of each coset is actually the same as the cardinality of the subset. Furthermore, if we define an equivalence relation on elements of G by them being equivalent if and only if their cosets are the same, this is an equivalence relation, right? So it's an equivalence relation because it's based on equality. So this is reflexivity just based on the reflexivity of equality, symmetry based on the symmetry of equality, and transitivity based on the transitivity of equality, right? This is an equivalence relation. What are the equivalence classes though? If we take an equivalence class, we see that if Y is in the equivalence class of X, then there must be some elements of the subgroup H for which YH equals XH prime, okay? If we cancel out H to the right, we see that Y is X times some element of H. This means that Y is in the coset X times H, right? The other equality or the other inclusion follows similarly, which means that the equivalence classes themselves are the cosets. This means the union of all the cosets is equal to G. Okay. The cosets each have cardinality of H, and the set of cosets partitions G. So their union is equal to G. So the number of elements is actually just the sum G slash H cardinality times of H. So this is true. And if we just divide H on both sides, the cardinality of G/H is just G divided by H. Okay, and so actually what this means, since G/H is just the number of cosets, left cosets of H and G, this means that for any it has to be a natural number. Okay, and so this means that the cardinality of any finite subgroup of a finite group has to divide the cardinality of the original group. And right, so groups have kind of this very symmetric or combinatorial nature. And the fact that we can describe symmetries in terms of groups actually allows us to talk about symmetries in the language of groups. And what this means for combinatorics is that we can, if our problem entails counting symmetries, we can actually use group theory to count those symmetries. And if we have five to 10 minutes to spare, I would like to walk through a problem. And I'm going to log in using my iPad so I can share my screen. And we can do some math, but just so far, does anyone have any questions or about the presentation? We're almost done, don't worry. Okay. So let's see if I can share my iPad screen. Let's see, share screen. Okay. Right, so does everyone see my iPad screen? All right, cool. Let me turn off the volume. Okay. So let's talk about the following problem, right? So imagine we have an airplane. Let me draw the best airplane that I can. It's too high up. Imagine we have an airplane. Okay, and this airplane can seat 100 passengers. Okay, just use your imagination to imagine this is 100. Okay, so 100 passengers. And there's no ordering, right, in which the passengers have to sit. And so they're all called to just stand in line. And what happens is that the first person in line, passenger 1, is a bit of a jerk and decides that they're not going to check what's on their ticket. They're just going to pick a seat at random and go sit there. Okay. And so there's equal probability. There's no, it's not like, oh, I'm just going to sit in first class. Every seat is the same. And the first person just picks a seat at random, right? Now, the second person has to either find the first person sitting in their seat, which would mean that they would have to pick at random, but they're not a jerk. So if the first person hasn't picked the second person's seat, the second person is just going to sit where they're assigned. Okay, and this keeps going all the way to the last passenger. So passenger N goes to the airplane and looks for their seat. And if their seat is occupied by a previous passenger, they sit down wherever, it's just a random seat. And if it's not occupied, they just sit where they have to sit. Okay, so the question is, what is the probability that passenger 100, so the last person in the line, sits in their assigned seat. Okay, so what do we think? Any guesses? And for anyone who already knows the answer, please don't answer because it's really cool. No spoiling. Less than 10%. Okay, so someone says less than 10%. Okay, so does anyone else have a guess? One over 100. Okay. Okay, so let's work through it, right? All the passengers have an assigned seat. So there's a function that gives us the seating arrangements that are possible under this scenario. Okay, so if person number 1 sits at their assigned seat, then person number 2 finds their seat vacant. Person number 3 finds their seat vacant, and so on and so forth. And everyone sits where they have to sit. If person number 1 sits in 2's seat, then 2 has to pick a random seat. And it can't, it can't be their own seat, right? So it has to be a seat that's not occupied. Let's say 4. So now person number 4 has to pick a random seat, let's say 5. And let's say 5 picks seat number 1. Okay, but now that 5 has picked seat number 1, seats 6 through 100 are open. So everyone else is gonna sit where they have to be sitting. Okay, but what's happening here? This is a cycle, right? So we can just write this as 1, 2, 4, 5, and 5 maps back to 1. And so this is just what we were talking about. Now the set of all the possible seating arrangements, is a set of these permutations. So now we just have to count how many of these permutations are possible seating arrangements. Okay, so obviously these permutations have to start with the number 1 because 1 is the first person to pick. And if it's the identity, right, it means everyone sits where they have to sit, right? It could be 1, 3, 5, right? And then 5 maps back to 1. Can we have something like this? 1, 2, 5, 4. Is this possible? What would have to happen for this to be possible? Right? 1 has to pick seat number 2. And then 5 has to pick seat number 4. But then 4 has to pick seat number 1, which kind of implies that 4 came in after 5, which is, contradicting the way that we're labeling these passengers by their place in line. By the time 5 picks a seat, 4 already sat where 4 had to sit because 4 came before 5 and found the 4th seat vacant. Okay, so this does not work. Right, so kind of the only way for a permutation to be a valid seating arrangement is if the elements of this cycle are strictly increasing. And so here's where we find something cool. How many increasing cycles are there starting with 1? So they have to start with 1. Okay, but how many increasing cycles starting with 1 are there? How would we approach this question? Oh, and by the way, I should mention, these have to be cycles because if there's some other cycle, right? Apart from the one that starts with 1, right? Let's say like we have 1, 3, 4, and then 2, 5. This means that 2 found their seat vacant, but decided to choose seat number 5, which goes against the philosophy of all the other passengers who aren't jerks. Okay, so this can't be the case. We only have 1 cycle. Okay, so how do we count these? Well, we can kind of do this by imagining smaller airplanes. So what if the airplane only had 5 seats? Or actually, let's make it better. Let's do 4 seats. Okay. What are all the possible seating arrangements? So there's 1, and this is just the identity. Okay. There's 1, 2. There could be 1, 3, or 1, 4. Oh, see you, Ibrahim. Okay. There could be 1, 2, 3, 1, 2, 4, 1, 3, 4. And then there's 1, 2, 3, 4. So anyone notice something? What are the valid seating arrangements where 4 sits where they have to sit? Well, it does have to do with subsets, but what is the way to tell from a cycle notation if 4 sat where 4 had to sit? The cycle doesn't contain 4, exactly. And so let's try to write all of the cycles that contain 4 on one side and all of the ones that don't on the other. Okay, so we have, these are the ones that don't contain 4. And I'm going to write this in a kind of suggestive way, but you'll see. This is 1, 4. Right? So does anyone see it? The cycles that contain 4. Yeah, so the cycles that contain 4 are just the ones that don't have 4 with just 4 plopped into the end. Right? And so if we continue this up to 100 seats, the cycles that contain 100 are going to be just the ones that don't contain 100, with 100 at the end. And so half of them contain 100 and half of them don't. Yeah, so the probability is a half. 50%. Okay, so I hope you guys enjoyed this presentation and learned a lot about some combinatorics and group theory. And if anyone has any questions, I'd be happy to answer them now. Or else, have a nice day.